Okay. Well, so um, today I'll try to explain you a little bit about the work we've been doing for the last few months. Okay, so the title is Detection of Magnetic Signals from Nanoscale Non-Stationary Samples. Okay, so well, the goal will be that you end up with a quite general idea of the work rather than giving a lot of detail that typically end up being too much to digest. So I'll try to be general and rather basic, but if you want any detail, just ask, okay? And I'll try to explain. So let me first highlight the two properties of the samples we will going to target that will kind of guide the talk. First, we will be targeting nanoscale samples. Okay, so those are samples with a rather small amount of particles in them, small compared with macroscale samples, of course. Still a quite big number, but and non-stationary samples, meaning that there is some kind of process going on in the sample that causes the amount of nuclei, the concentrations to change in time. Okay, and well, let me also advance that, well, surprise, surprise, we'll be using NV centers to detect these kind of signals, okay? I had to include the guy in the presentation. Okay, so this is the kind of setup we'll be dealing with. Okay, we have a sample that contains some kind of particle with a spin. I'll typically say nuclei, but it could be also electrons, any particle with a spin. Okay, so let's first consider a sample of millimeter cubed volume. And in this regime, in the absence of any external influence, the orientation of the spins just cancel themselves. And as a result, there is no magnetic moment in any direction of space. But if we apply an external magnetic field, the spins tend to align with the field. And there is an imbalance between spins pointing in the direction of the field and against the direction of the field. The result is that there is a magnetic moment that can be used to extract information from the sample. And the typical approach is to apply some pulse to the sample that tilts the magnetic moment to the orthogonal plane with respect to the external field so that it rotates and emits an oscillating signal. And detecting this signal, well, is the typical standard NMR technique, okay? Let's now consider a smaller sample, like a micrometer cubed volume sample. Now the amount of nuclei is smaller, of course, and as a result, the imbalance between spins pointing up and spins pointing down is also smaller, so the magnetic moment is smaller. And the emitted signal will be weaker. In this regime, the signal-to-noise ratio begins to be too bad for classical NMR techniques to detect these kind of signals, okay? There are experiments that have detected signals from samples of 3 micrometer cubed samples, but those are quite elaborated and quite complicated experiments. So if we go even smaller samples, nanometer cubed volumes, we'll have to find a different approach to detect signals. And well, as I've already told you before, we are going to use NV centers. Well, the magnetic moment is even smaller, of course. And the approach will be to place a diamond near the sample that contains a single NV. It could be more, but let's consider it's a single NV. So this NV is sensible enough to the magnetic field in order to detect the weak signals that are generated in these rather small samples. Okay, so This system is described by this Hamiltonian. I am not really interested in the details of the Hamiltonian, but well, just briefly mention that the first part describes the dynamics of the MB. Second part describes the dynamics of the nuclei. And here we are not considering interactions among the nuclei, just because they happen in a different time scale and we can forget about them. The last term is the dipole-dipole interaction between the MB and each of the nuclei in the sample. And this is the term that allows the MB to gather information, okay, from the nuclei. Well, working with this Hamiltonian is a little bit complicated. So in order to simplify it, we go to an interaction picture with respect to the free dynamics of the MB and the nuclei. And we end up with this rather nice-looking Hamiltonian, where we just have the interaction of the MB with the field generated by the nuclei in the sample. So what is the form of this field that we want to detect? Well, first, we have to note that in this nanoscale regime, the thermal polarization, even at room temperature, is negligible. Okay, so we won't have this contribution. And it's negligible because it is very small compared with the dominant polarization in this regime, which is typically called statistical polarization, right? And you can think of the statistical polarization as some kind of a finite size effect in which the amount of nuclei is not big enough to compensate all the polarization in all the directions, okay? So as a result, and even if the average polarization is 0, it fluctuates a lot, and instantaneously it may have a given polarization at some direction in space that will cause a given some magnetic moment. For example, this one. This magnetic moment has an orthogonal component to the external field, so it will rotate and emit a signal. Okay? After some time, it will fluctuate to a different polarization in a different direction. For example, that one, which again has an orthogonal component. It's smaller, so the signal will be weaker, but it will still emit a signal. And again, after some time, it will fluctuate, blah, 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 it will rotate, emit a signal, and so on. Yep.
And why does it fluctuate after some time? It's as a result of the statistical polarization?
Yeah, let's say it's due to the internal dynamics of the sample. Spin, relaxations. This fluctuation is not, this picture is quite naive. It's not, it's easier to see it that way, but we don't expect these kind of sudden jumps. It would, but I think it's easier to understand the fluctuation and how it, but it's not rigorous at all. But, well, if one wants to be rigorous about the signal we are targeting, well, there you have it, the signal. Okay. Now, even if we were able to detect this signal, then extracting information with this kind of expression would be at least hard. So we can work it out and simplify it considerably and arrive to this kind of expression, which looks better. Okay, but this derivation is not straightforward, and in fact, well, it has caused some headaches in our office for some time. We have been struggling with it for some time, and going through the derivation, obviously, it has no sense here, but I will give you like the main ingredients. First, you start by assuming that you are going to drive your MV with certain control sequence. This basically allows you to either discard this odd oscillating term or this even oscillating term, depending on the symmetry of your driving. Then you perform a semi-classical approximation. That basically means you exchange the operators by the expectation values. This, what it's telling you is that you won't have a back action from the dynamics of the MV in the sample. Okay, so even though if they are interacting, there won't be any entanglement and so on. And this is valid in a regime in which the external magnetic field is bigger than the coupling between the NB and the nuclei in the sample. Okay, and we are in this regime, so we can do it. And finally, if one does these integrals, you can see that they vanish. And this confirms what I've told you before, that the average polarization in the statistical polarization regime is 0, and therefore the average emitted signal is 0. But it fluctuates a lot, and we are targeting the signal emitted by these fluctuations. Okay, so we'll have to compute the deviation of the field, not the average. And well, already in this expression, it's easier to read the information, basically because the amplitude gives you the concentration, the amount of nuclei that it's emitting this signal, and the frequency gives you the information about the type of nuclei you have. Each type of particle rotates with a characteristic frequency around a magnetic field, so identifying the frequency is just identifying which kind of nuclei we have in the sample. Okay, so we've covered the first part, the nanoscale part. Let's now focus in the second part. So, as I've said before, we consider that there is some process in the sample going on, right? And as a result, the amount of nuclei evolves. What we want to do is to identify that evolution in order to characterize the process that is causing that evolution. Okay? But, well, having a non-stationary sample, that basically means that the signal that you detect has a time-dependent amplitude. Well, it makes extracting the information a little bit trickier. So to see why, let's consider the stationary case. Okay, so if we have an NB interacting with this kind of signal with constant amplitude, we can compute the expectation value of the sigma x operator, which is the observable we are going to be measuring in the experiment. And if one plots this expression for different values of omega, which is a control parameter, is the frequency of the driving that you apply to the MV, you get this kind of plot. And in this plot, it's really easy to identify both the frequency, because the lowest point is when the signal and the driving are tuned, and the amplitude from the depth of the graphic. But let's consider what an experimentalist would have to do to obtain this kind of plot. So you tune the frequency to a given value, okay? Let the MV interact with the sample, and after some time you measure the MV. But when you measure the MV, you don't get the expectation value. What you get is either a 1 or a 0. That are the eigenvalues of the eigenoperators of the observable you are measuring. So what you have to do is to repeat the experiment a lot of times. And only by taking the average, you get the expectation value that you want. So each of the points in these plots correspond to an average over a lot of measurements. But if the sample is evolving, meaning that the signal is evolving, the first measurement, so if we repeat the same experiment and we set a frequency, let the system MB evolve with the sample and then measure, the first measurement corresponds to some value of the field, of the signal. The second one to a different one, and so on, and so on. So in this scenario, taking the average of the measurement outcomes it has no sense. I mean, you can still do it, but you won't get any information out of it. So this approach is not valid here. Okay, so what do we do to extract information from these measurements? Well, so we'll use what this gentleman here wrote down more than, I don't know, 250 years ago or so, more than that. This is Thomas Bayes, and this is Bayes' rule. And this is quite a simple expression, but at least in my experience, quite powerful. And it just relates the probabilities of two different events, event A and event B. Okay? And it could be quite useful if we identify event B with the parameters that define your system having certain value, and event A with the data you obtain from measuring your system having certain value. And in this framework, what Bayes' rule provides is a way to update the information you have on your system based on the measurements you are doing on it. So to see how we apply that in our problem of detecting this magnetic signal, we are going to consider a particular example. So we consider, well, first let me just mention that you need some kind of information about your system before you start. So you start by modeling your system somehow. If you don't have any idea of what is going on in your system, you just invent the model, and then by applying the Bayes rule, you'll see how good or how bad the model is. But if you have some idea of how the system is evolving, well, then you can model it better from the beginning. So, as I've told you, we are going to consider that the amount of, yeah.
Actually, that's really the point, to my understanding.
Mm-hmm.
Neural networks are good, right? Because from my point of view, my experience, Bayes is very powerful from the statistical point of view of extracting information on these things, but you need to know the model, right?
I don't know. That there are, I think, quite advanced like multi-model bias analysis, and so that really tells you not only the probabilities of the parameters having certain value, but also the probabilities of this model being the correct one or this one. Like, there is a lot of work here.
All right. But then in the case of having zero, right, models about
Yeah.
the power of a neural network, classical neural network, is essentially to establish a relation between inputs and outputs, right? So in this complicated structure, the model is there, right? In some way, you provide, you feed the neural network with enough data, right? Okay.
Yeah. So you use. Yeah. You mean that the neural networks is able to find the model in his own.
You never see the expression.
Yeah, but yeah, he finds a way. You don't have to.
Yeah, but of course, maybe what I'm saying is too general, right? So
Yeah.
I can imagine that also. Because I mean, some people is also introducing neural networks to calculate actually this EAB, right? The likelihood. That's another approach in case you don't mind.
Yeah, because the model is just to be able to compute that.
Exactly.
Because the rest is just like the the prior probability distribution. I mean, if you know nothing, this probability is just a flat probability, and you can work with it. But computing the likelihood is the...
Actually, you are doing that, right?
I feel that the neural networks can give you very wide probability environment. Here, they try to should work on some specific things. You have to know enough pre-knowledge.
And for the applications we have in mind, that I've mentioned briefly at the end, there is some knowledge about the system. Either you want to use this as a verifying tool, or you suspect what is going on, but you don't start from zero, let's say. Okay, so back to this particular example, in which the amount of nuclei decays exponentially, okay? So we simulate the interaction between the MB and the sample as fairly as we could, also the simulation process, and we end up with this kind of data set that contains the measurement outcomes, okay? And well, basically, applying bias is going from a prior probability distribution that, as I've said, it's going to be a completely flat distribution, meaning that we have zero knowledge about the values of the parameters. We compute the likelihood, that it's just the probability for a given value of the parameters to obtain the actual data set that you have measured in the lab. And you end up with the posterior, like updated probability distribution. Here you have a couple, well, one example for the two parameters. Okay, the orange dashed line is the prior distribution, and by applying bias, one can get the blue distribution that already assigns like a higher probability to some values and a lower probability to other values. But two things here to mention. First, with this kind of distribution, we are still far from knowing exactly what the evolution of the system is. And second, this is just one example, one case. But there is a lot of stochasticity in the process. So it could be that for the same process, the data set we end up with results like good for bias or bad for bias. And we will be interested in knowing the performance of this Bayesian analysis in average, not only for a given case. Yep, please.
Is there any possibility from the cases that you have studied where you have not this dynamic behavior of the sample, you can initialize somehow the prior distributions of bias?
Yeah, so start with a prior distribution that is not flat. You mean that you have some information at the beginning. It could be, but you'll, with the results I'll show you later, you'll see that we don't really care about starting with a completely flat distribution. And, well, I don't see how, I don't see how we could like use arrive to a better prior distribution, but maybe we could. But the results are already really good, starting with this kind of flat prior.
The best result is, that we can achieve with our method is to say, okay, at the very beginning we know nothing, right? We have absolutely no idea which are the time scales of the process we are studying, and after we apply our measurement, we really see a distribution fit that some specific, right? So starting from zero knowledge to a very, let's say, deep knowledge of the cases. That's the result, right?
Also, I think like that The idea we had in mind is that we have one sample that evolves. So we cannot make repeated measurements in that sample, so in order to obtain a prior information about it. We just have one sample, we repeatedly measure it, and from this data set, we want to extract the information. And that's all. That's the framework we have in mind. Okay, so what was I? Yeah. We want to know the average performance, let's say. For that, we defined these two quantities. D is the distance between the mean value of the posterior distribution and the value of the parameter that has generated the data. Okay, so how close or how far we are from finding the actual value, and sigma is just the width of the distribution. So for both quantities, the closer they are to zero, the better. And we simulated a lot of the times the same process, applied bias rule for all of them, and those are the results we obtained. The red line is a single MV, and basically using the most basic control sequence that one can think of. So it's always away from zero. Those are plots for different values of the initial amount of nuclei. Okay, just because we wanted to see how weak of signals we were able to detect. But well, so the red line is far from zero at all times. But as I've said before, it's kind of the basic approach, and there's a lot of room for improvement there. And a possible way to do it is to consider more than one MV. So we considered an MV ensemble to detect the signal. These black lines correspond, I think, to 1,000 MVs or so. And you can see here how, well, beyond some limit of initial concentration, we are almost at zero at all times, meaning that we are with almost complete certainty, we know the evolution that is going on in the sample. And yeah, well, that was basically all. If, let's say, 3 weeks from now you remember like these 3 basic ideas, I'll be more than happy with my work here. We've combined the use of MV centers to detect signals that come from samples that are too small, so signals are too weak for classical NMR techniques to detect. And we have combined it with the Bayesian analysis to extract information from the measurement outcomes. With this, we have demonstrated that we are able to identify the evolution of the concentration of atomic nuclei, but it could be also electrons, in nanoscale samples. And hopefully, with this information, we are able to characterize whatever process is generating this change. And well, currently we are having some conversations regarding some specific applications. One of them is people that are interested in characterizing chemical reactions that involve radicals, so electrons that carry spins, and therefore we can detect them. And by identifying the evolution of the amount of radicals in the sample could be used to characterize these chemical reactions. This looks promising from now.
The application is strong there, right?
Yeah.
Essentially, people would love to characterize chemical reactions with some samples involving a very reduced amount of nuclei, right? Because
things are cleaner, right, in a nanoscale sample.
Yeah, because essentially what the people is looking for is to characterize the mechanism of reaction, right? And that's something that cannot be done at all in macroscopic samples because it's essentially too complicated.
It's a lot of noise, a lot of
everywhere.
Different kind of particles.
However, you will not the samples, meaning that you are totally out of standard NMR techniques. Probably we could start watching what happens at the nanoscale level, right? To start characterizing which are the mechanisms of a certain reaction, chemical reaction.
So in these cases, they have an idea of what is going on. So what I've told you before about the model to compute the likelihood, but they are not sure. So it could be a nice tool, the method that we have developed. And the other one is people that they are interested in like verifying the decay rate of radioactive nuclei. But well, this application is slowly developing yet. We are not. We don't know. Yeah.
To take a sensor really to locate at the surface progression of radioactive substance is not so easy or so nice, right? But for example, the first case is even, I think the application really is key, right? Because it seems that in the first case, in the case of chemical reaction, you could even initialize the reaction at your region, right?
Optically.
Optically. So you can initialize the reaction optically. Type of laser we need for initializing the engine.
Yeah, you can synchronize everything pretty good.
The other case, is more fundamental, right? But I mean, while in the first case we already have application, in the second case, radioactive is something like, okay, something to be explored, right?
Yeah.
But that second part is not so. It looks interesting, but of course I can imagine that people that make nuclear physics have also their methods.
Yeah. From the conversations we've had, I think that they see this like a verification tool. Like they have other methods and they know the rates, but maybe this is more precise, maybe not. Maybe it's just a way to verify it.
Actually, I was discussing with some guy that probably is coming in some weeks, right? I think actually it would be nice to observe, to see what happens, for example, to be able to calculate the amount of some radioactive substance, for example, in some substance taken from the body right after radiotherapy. Right? Probably this appears there in very low quantity, with very low concentration, which again is totally out of the
classical
NMR. Right? But still, I can imagine this is complicated.
Well, that was all. Thank you.
At some point, I lost the connection between the Bayesian analysis and the MB centers as a magnetometer. So what you're trying to do with this analysis is to analyze the signal that the MB receives and get information about what the population of the nuclei or you can do that connection.
Joder, qué pequeño se ve aquí. Pop. Okay, so with the MB, what we achieve is this. This is just measurement 1, outcome 2, In each of the operations is just driving your MB, letting the MB interact with the sample, measuring, and you get a 0 of a 1. Actually, it's not a 0 of a 1 because the way you measure an MB is more complicated, but well, to simplify it, it's just 0 of a 1 or a 1. And then what you do with bias is extract information from this. So up to this point is just MB working as a magnetometer. And once we have the data of all the measurement outcomes, then it's like information processing. You use this to update your knowledge on the system, basically to update your knowledge on the decay rate and the initial amplitude. So yeah, the goal is to find as precisely as possible these two values, the decay rate and B0. Of course, if we propose this kind of exponentially decaying model, but the system is not exponentially decaying, we are going to find very bad results here. And we will have to say that we are wrong. The model of the system we are using is not wrong. And try a different one. But yeah. Yeah.
The thing that I would ask for the exponential decay, because why there is an exponential decay? Because you start to say first Vn, it was a cosine.
Yeah.
And then you put
the exponential decay is the amplitude. So it will be like an envelope to the. We still have the oscillation. It's just the. Esto va para atrás y lo hago así. Oh, qué bien. Here, for example, I'm just plotting the amplitude. So if I plot the whole signal, it will be an oscillation with this kind of envelope.
So you see experimentally, no? Or there's something.
The exponential decay is more of an example that we have made up, let's say, to demonstrate that we were able to use bias to be really precise in identifying the evolution. But you can think of a lot of processes that generate an exponential decay. For example, the radioactive decay that we've mentioned, it could be modeled this way. But yeah, so far we have like no experimental support so far.
It could be the other way. Maybe you have a substance that is appealing to a chemical reaction, and then you go the signal.
Yeah.
It depends on the case.
Yeah, it's just an example, but it's just a matter of modeling your system, the way it's actually behaving.
This is about the MVs. You say that you use 1,000 or more than MVs. They are connecting the same way. You can put them really close to the, because you have a lot of MVs, very probably there's more than farther than others.
Yeah, nice question. We are in an homogeneous regime, so all the MVs see the same signal. There is no difference due to depth, for example. But, well, yeah, we are in a regime of sensor volume that is really small, and NV concentration that allow us to first neglect the interaction between the NVs, and then assume that all the NVs see the same signal. So we are in this regime. Yeah, the phase is something that I've not mentioned during the presentation on purpose, because it's been to actually this in the statistical polarization regime. Let's go back. A second. Okay, here, in order to arrive to this expression, this phase has to fluctuate randomly. And basically, what we have to do when we compute the likelihood is to integrate over all the possible values of the phase. Why is it randomly fluctuating? Well, this is hidden in this box here, and I don't want to enter there too much. But yeah, at the end, it doesn't matter a lot. We just have to integrate over all the possible results and obtain an expression from there. It's actually an integral that we can do it analytically.
So the variation of phase does not matter too much.
What, sorry?
I mean, the variation of phase does not matter too much
No.
about your signal.
No. So in order to model this kind of complicated signal like this, we have to introduce here a fluctuating signal, but it doesn't matter because we just integrate.
But this is because the nature of the signal we are
Yeah.
similar to things we are doing with experimental tiny groups where this phase is essentially constant and coherent. Right? In that case, because of the nature of the signal, so I mean, you can imagine that each ND, I mean, we have an ensemble, and each ND is watching actually a very reduced amount of sample, right? And in that sample, you have some amount of nuclei, which is pretty low, typically, I don't know, thousands of nuclei. Could be.
Yeah, 10,000 or so.
Yeah. But I mean, because of the diffusion, I mean, that nuclei contributes to have, for example, a polarization defect, right? But some of these nuclei can abandon this volume and enter new ones, right? With a different polarization that would randomly make rotate, for example, the polarization, right? So this is reflected actually in this phase, right? And on average, the amplitude that we take as the variance, right? And well, these are several assumptions that it seems to work.
It seems, yeah.
Yeah, that's the point. So, I mean, perhaps in this work, one of the, just to clarify the concept, because this is pretty complicated, right? Essentially, what we are doing here is to try to scan, right? Typically in quantum mechanics, right? So what you do is to prepare an initial state of the whole system, right? Imagine you have tons of qubits, I don't know, 20 qubits, you prepare initial state, you leave the system evolve, and you measure, right? And you back, you initialize again the time, right? And you convert it and you get some expectation value. That's standard procedure. However, here, because of the nature of the signal I want to analyze, for example, imagine I don't know some radioactive substance which is decaying, right? So this means that the amount of substance the concentration is changing, right? Because of the evolution is like that. So that means that we cannot initialize the system back to the origin. So essentially, we just have a time window in which our signal is evolving and probably vanishing, right? So in that time window, so we have to adapt the only thing that we can initialize, which is the ME, right, or the sensor, or the ensemble of sensors, and develop some statistical methods to assuming that essentially we cannot obtain average values, right? From that, essentially, it's a list of 0 and 1.
Yeah.
I guess it's a list of number of photons in the end, right?
Yeah.
0 photons.
Between 0 and 5, 6.
Yeah. From that mesh, right?
Yeah.
You would like to estimate properties of the substance which is generating that signal that cannot be initialized, never, right? Because it's, as soon as you start the chemical reaction of the nuclear decay, so you cannot take the whole system to the very beginning to replace and to start doing average values. So that's more or less.
Yep.
Yeah, a question about this control parameter. Do you choose just one omega, or do you choose, or can you take several omegas for your analysis?
We assume that we are tuned with the signal. So we assume that we know nu, that is the frequency of the signal, and we are tuned with we tune the driving frequency to be that. But in principle, this is because, well, we didn't want to complicate too much with the Bayesian analysis, but we could, in principle, set nu also as a parameter, as a model parameter that we want to identify, so as an unknown parameter. But here in this example, we assume that we know the frequency. Yeah. I guess that once you increase the number of parameters, doing this Bayesian analysis thing gets complicated, and you start to require numerical methods like Monte Carlo sampling, blah, blah, blah. That's, for now, we avoid it. Yeah, yeah.
So you're exploring only to be plain, and now you
Mm-hmm.
that complicates a lot.
Yeah, we kept the things simple for now. Mm-hmm. Okay. Mm-hmm.